There's a little place left for you. What do you know? What do you know? And all I want is to find out what you're going through. What do I know? Maybe the silence is dangerous.
What's up everybody, I am back with another video. I know you guys have missed me, so I thought, you know what, it's a Sunday, let me make you guys a video. We're going to be covering let's say next level work. It's not really the basics anymore. We're going to add on to some topics like the black bolts and deciding on your batten sizes. And then also we're going to look at this drawing here in front of me now, which is what I'd call like the worst case scenario if you were to calculate ridges, because none of these ridges line up. And you know, if you don't have the tools to figure out what the hell's going on with that little ridge, you're going to have a really rough time. So I thought I'd share my findings on this drawing. I'm going to start firstly with the wall plate, because I don't think wall plates are too straightforward, and I mean they're a bit underrated because they're not outwardly tricky, but if you slip up with designating where your wall plate starts and ends, you're going to be in trouble. So I'm just going to break this one down. Your wall plate on this side is going to run, and you can choose to either stop on the inside face or follow it right through. But I would say if you're going to follow a rule, you must follow it consistently. So for this drawing, let's just say that horizontally it's through. Oh, sorry, vertically it's through. So well, vertically as in we're looking at the drawing now, bottom to top, we're going to measure straight through to the other side. Okay. And horizontally we're going to measure short. Okay. So if you follow these rules, you should be fine. This is the gable end on this side, so you obviously don't measure wall plate for that. There is no sort of roofing structure going over this gable end. The only thing that you need to be cognizant of is when you come to your flashing, you're going to have to put a flashing along this gable end, and it's going to be multiplied by the same slope factor that you found previously, which will be 1 over cos, and then over here your pitch, which is 28 degrees. So back to the wall plate. Vertically through, horizontally short, you apply that right around. Okay, and you've got to add up each calculation. Horizontally short, I went over there, but I'm just going to draw straight over it now. There we go. Vertically through. Remember, it's only on the inner skin, so don't go that far. I guess that's fine. Horizontally short, like that. Vertically is going to be straight through again. Now here's interesting scenario where you're going to go across, and when you come to horizontally short, it looks like it's longer. And that's because the cavity doesn't extend straight through. So this is another trick area, in this drawing at least, is that if you look carefully, and I'll try and zoom in for you guys here. Okay, let's take a look here. You're going to be horizontally short, and you start where we ended. But now, that's the end of the cavity, okay? And let's just do, for the sake of argument, let's say you're applying the rules very strictly without actually looking at what you're doing. Now you're going to do your vertically through. So we're going to start at this gable end, run all the way through, and you have not covered the entire wall. You've measured your wall plate short. So the issue here is that when there's a sort of, I'm not too sure about this theory, but when there's like a cutback where the measurement has come inside and then back out, your inside wall plate is now kind of acting like an outside wall plate. It's now a kind of a perimeter. So if you take a look at this, it's now like an outer perimeter. Let's take a look at this case example here. If you were to measure the outer perimeter, you measure vertical through and horizontal short. That's what it would look like. So you see, it doesn't work for outer perimeter. You've got to include that cavity. And now we sort of ignore this sort of phenomenon when you come to outer skins, but it's going to catch you out here, because this is kind of an inner skin acting like an outer skin with regards to perimeter. It's a very interesting case here. So you've got to add that piece there, guys. You have to add it. That is about it for that drawing. So there's an extra 50mm that you would have probably left out. Or, yeah, if you weren't looking carefully, you'd say, well, something weird's going on here. You're going to put in a 50, but you don't really know what the hell. Well, this is it, is that, and I stand corrected, but something happens when the wall cuts back on itself. You know, usually it would just travel through, and then like that. And in that case, your inner skin would carry on running in this direction. It would go over, so your horizontal would be measured through, and then your vertical would be measured short. There would be no sort of mysterious force at play, except if you have a cut back. Then something weird happens. And it's kind of behaving like outer skin. So I hope that was interesting. Let's move on to, I want to speak about the ridges, because there's an interesting sort of logical game going on here. You don't have all the information for your ridges. What you do have is the knowledge of your sort of, let's call them widths, your widths of roof. So that's a width of 4,250. You don't have this width on this end. You have a width here. Sorry, it's actually not 4,250. You got to add the overhangs as well. Okay, just remember that. So this width is 3,800. Okay, and this width is, well, let me just draw it nicely. 5,050. Okay. So we're collecting evidence slowly but surely to help us figure out, you know, how we can extend this evidence to other parts of our drawing. This 5,000 here is not sort of obvious how we can use it. So what I'm going to do is make it a bit clearer. We're going to convert this, maybe you'd consider this a length. We're going to convert it to a width, and it will help us just now. It might not be clear yet, but you will see. So that is 5,000 plus these two 400s minus this 1,500. Okay, so it was 5,800 minus 1,500. Okay, that's that entire, sorry, that's that sort of shortened length, which is now a width. Okay. Okay, so we have totals. We have sort of totals for sections. We know what this section span is from there to there. We know what this span is from there to there. And finally, we know what this span is from there to there. So we are making progress. Now you're going to say, Anthony, why do we need that? Well, there's something going on here with our ridges. And these are called perfect square isosceles triangles. Okay? This is a 90 degree, that is a 90 degree, and this happens to be a 45. And what this means is that this triangle has the same lengths. It shares the same lengths. That is a property of isosceles triangles. That these, and remember, we're only talking about on flat at the moment. Those, sorry, let's not make those x's. They don't all, yeah. So, well, actually, it is the same. Right. So that's what rule we're going to take advantage of here. Is that okay? That's a 45. Those x's must all be the same. And since it sort of cuts this ridge in half, what can we say? We could say that x is half of 50 or 5050. So x equals 2525. X equals 2525 on flat, guys, on flat. And I'm waiting for someone to say, well, you know, you're wrong. And yes, it's wrong for now. It's just on flat. Once we've got that, you can start seeing the picture come together. And you'll say, well, we can now start converting based on more information down here in our description. What do we need from the description? We need the pitch, and that's about it. Okay, the pitch is to 28 degrees. So to convert any value to a sloped value, let me change the color here. What do we want? Purple. It becomes 2525 times 1 over cos of your pitch, which is 28. Okay, I'm shortening the sort of the trig calculation. You should know the longer version by now, but I'm shortening it to save time. This will give you a value for it on sloped. And then what you do from there is the same as you have done previously, is that you've now got this on sloped, and you've now got x over here on flat. 2525. So what you do then, let's just clean up so it's a bit easier to just erase that side. Then you say, well, this I can see, that's root. So this is just Pythagoras, 2525 squared plus whatever this value is, 2525 1 over cos 28 squared. Very messy, but you understand what I'm doing, and that'll give you that length. Okay, once you've got that, you can move on to your other triangles. So let's just take a look. This triangle is going to apply the same rule, but it's going to use a different width. And you must be really careful as to which sides you're using. This, so you've got to visualize, and you can kind of see which goes where. And let me just explain what I mean by which goes where. This corner goes to that side, okay? This corner goes to this side. And you can see, because it's cutting it in half. You can't take, let's try and make an example here. You can't take this corner and then go to this side. It is not going to work. This corner, you can clearly see, does not reach the center line of this ridge. Okay, it's short and it cannot apply. Okay, so then you're going to say, well, Anthony, how do I do that one? Oh, okay, we're going to get there. So that ridge to that side, these ridges you're going to apply to this width here. Okay, the same for this valley is going to, basically, you don't even have to calculate the valley. It will be the same as these other ridges. You're just going to copy that value that you found there. And we'll get to this one. You're going to apply back, all the way back down here to this width again of, what did I say it was? 5,800 minus 1,500. So this was 2,300 on this side, right? Okay. So that is that. I don't think I need to go over it anymore, but what you're doing is dividing the drawing to a bunch of triangles. You're being very specific as to which triangle goes to which width. Okay? Do not mix them up. Don't send the one triangle to the wrong width. Your calculations will come out wrong. Okay? And that is it with the ridges, or at least the valley and hip ridges. Then you're left with asking, well, Anthony, thank you for the help, but it's not enough. Why? Well, you were looking at ridges, but we've missed this little piece here. Okay, this little piece here. And as of yet, we haven't actually calculated the top ridge. We've done the hipped ends, and the valleys would be done by now, whether that be a valley rafter or a hip rafter or valley lining, or that's all the same calculation, the same value. But we do not have these short little pieces in the center here. They're still outstanding. Okay, and this is where it gets even more complicated. I wouldn't say complicated, but you have to see it. If you don't see it, you're not going to know how to do it. So what I did is you're going to say that a triangle takes you to a certain point, and another triangle takes you to a certain point, and you're going to add the triangle sides and then subtract it from a width. And then that wasn't a very good way of explaining what's going on, but you'll see now. So if we said this was 2, 5, 2, 5, right? From there to there was 2, 5, 2, 5. And if you've done this triangle, I don't have the value at the moment. Well, actually, you can take it from here. So since this width was 2,300, this is 1,650, right? And that means that this drops by 1,650 in this direction. Okay, so what we're trying to say is we really take advantage of this perfect triangle. We've taken advantage of its sides that happen to be the same. Okay, we're taking advantage now of this fact and the fact that we have a width. I'm going to say, let's say for this side, we want to know what this rise and run is. And I need to be careful, this place is really small. So let's just zoom in here a bit. Okay, so what is this last bit here? We'll call it X. So since we know what the width is, 5,500, let's do a little calculation here. 5,050. Okay, minus, and this is just basic sort of, it's not even algebra really. 1,650 minus 2,525, and that'll give you X, right? Let's say I rearranged it. And X comes out to, and I actually don't have that value, but you will get what your change in length is. And since even this little X triangle here, this little unknown triangle here, will also be a perfect right angle triangle. And that means you're going to apply the same rules. Again, if X equals A, B, C, so this bit here, come on, get rid of this. A, B, C. and this length here is also A, B, C. So that is unknown. That is your ridge. This is actually your ridge, Y. So we want Y. And you're really, really close. You've got ABC and ABC. And you're going to have to imagine it being a number. And you're going to say, well, what did we do over here with this giant triangle? We took Pythagoras of a value on flat, ABC, and then one of these actually had to be converted to on slope. So we went A, B, C cos 1 over 28 to convert it to on slope. And so you're going to do that again. A, B, C. Whoops. Cos 1 over 28. And you will get Y. Isn't that exciting? You've taken sort of values from the extremes of your drawing and you've brought it inwards and you've made it associate with something that wasn't really obviously associated. And now you can find anything. You've got all the tools basically. As long as you know these are all perfect right angle isosceles triangles, they're going to apply the same rules. The sides, these two sides are the same. Okay, and if they're the same and they cut a width in half, you're going to take the half, so this is divide by 2, you get the side. And once you have a side and you find the other side, you can find the last little bit in the middle, which would be Y. It is complicated, but once you wrap your head around it, you can solve anything really. And if you come to this little piece here, this little piece is a little bit different in that it's actually, it over measures and then the difference is in negative, but you can't have a negative length. So you make it positive, right? Let me just see. So you're working with this triangle here. Sorry. Let's start here. This triangle, okay, and there, okay, and what we're going to use is this width here, because we can see it's the closest, sort of the closest to what these two triangles will add up to. If you are, sort of what's the word, observant, you'd notice that these two triangles are a little bit over. Okay, this X here and this, well, let's call it Y because they're not the same, is a little bit over the 3,800. So we're going to do the game where, okay, we find our values for the sides. I don't know why I would make a different value, Z and Z, based on half of a width somewhere, right? So this 3,8, half of it would apply to the Z, okay, because you can see this ridge here. So half goes that way to Z, and then you're going to use a different triangle for these X's on this side. Let's use a new color so we can see what's going on. So these X's actually apply to a different width, which is on this side here, what we calculated as 2,300. So that's half 2,300, you get these X's. Then you do the same whole process of sort of finding the sides of our right angle isosceles. You apply them, then you get a length there, and then a length here. And there's going to be overlap. And that overlap is actually what we want. That tells us what's going on here. So we go 3,800 minus X minus Z. And that'll give us a negative number. Let's say it's negative 300 mils. Okay, so what does that tell us? Let's just zoom in. So green is not a good color. Let's change over to blue. Okay, 300 mils negative is saying, well, we had a width, but our triangles are actually bigger insides to the width. And the negative 600 is saying that it's over by 600 mils. And you can't have a negative length, so we'll say that this is 600 here. Sorry, I changed it to 600. Okay, it's 600 now. I hope you're keeping up. Okay, 600 there and 600 here. Okay, and now we're going to do exactly the same as we did here on this side. I have to scroll. Okay. And you're going to convert one side to slope and the other side is going to stay flat. You're going to have root 600 squared, which is still on flat, the one 600. And the other 600 will have to be converted to on slope, which is 600 times cos 1 over cos 1 over 28 degrees. Okay. Sorry, I think I've actually done it wrong here. It's one over the whole thing. Yeah. So you have to forgive me, guys. It's the whole thing. I just rearranged it in my mind and didn't really. Okay, so it's 1 over cos 28. I hope you picked that up. 1 over cos 28. Very bad maths. Okay. 28, not 25. Okay, the same thing here. I don't know why I did that. Sorry. So 1 over cos 28. We'll convert it. And once you've converted it, you now have this little ridge, which you can't see very well anymore. You have that little piece there. Okay, and you've got the other piece there. By now you would have calculated this hip rafter length, or tiled hip length, or maybe it's a ridge capping. Okay. Here's your valleys. You would have that by now. So you're almost there. You're almost there. The last thing to calculate for your ridges would be the long flat lengths. And again, not so straightforward. This is a tricky drawing, I'll be honest with you. Let's clean up before I... Okay. So we have this bit and that piece. We have all of our sort of on corner pieces that run from the corner up for our valleys and hips. Okay, so that's what we have so far. The flat pieces are not so straightforward. I'll start with the easiest one, is that 1500 applies to this outer edge, and since both these lines appear to be sort of parallel in that they both apply the same angle, let's say 45, it is 45, and so hold on, so since it's the same, we're going to say that this length is also 1500. Okay, so you get that, and you say, well, we're almost done. You're starting to get excited, but it gets quite a bit worse from there. This ridge here, I just need to take a look. You're going to make some deductions. Now this one's not too bad. Okay, so this ridge, you can see, is deduction of this x. And where does the x come from? The x is half of this 5050. Okay, and so you'll take this overall 7730. Just be careful to check these ends, okay, so it doesn't go over to the gable end. I'm happy with that. And it doesn't go over the 400, so you've got to add that 400 to get to this end. Okay, so 7730 plus the 400, and then minus the x. You've got to come back, and you've got to come back, and I probably shouldn't draw it on that triangle because you're going to get confused. It comes back to that edge there. Okay, 7730 plus 400 minus half of 5050 will give you x there and x there. Since they are the same, because it's a right angle triangle, it's going to bring it perfectly to that line. And you've got that ridge. And there's one left. And this is probably the worst one. Is, okay, we're going to make use of our triangles again. And the rule that they are equal. Sorry, not, yeah, equal lengths. Equal length right angle, isosceles triangles, right? Okay. This we can't use that one because it doesn't go all the way to the ridge, the end of the ridge that we're trying to measure. So you actually use this one here, right? Because it goes to this ridge point. Okay. So this one applies the half of, this was 2300, I think. And it'll put it there and there. So it's 1100. Was it 2000? It can't be 2300. I don't remember what this value was here, but just following on the logic, you're going to take this 10,500. You're going to, what did I do? Actually, let's back it up. Let's not take that 10,500. Let's take advantage of this value over here. 2,450. Okay. That says that from there to there is 2,450. And we're going to add on this triangle. Oopsie. So what I'll actually say is that it's gonna use the little piece that we calculated earlier. Okay. Because this is the triangle here, and you're gonna come back by this little triangle, the little triangle side. So this centerpiece is really tricky. Really tricky. It's 2,450 plus this side, we'll call it B, plus this side over here, which I said is Z, and then I want to subtract, and let's zoom in so you can see, we're going to subtract this tiny little length here, because it's going to bring it back. I want to come back so that it actually lines up with the ridge, and we're going to call it O minus O. Okay, that should give you your ridge length in the middle here. Yeah, so that's probably the hardest part to see about this drawing, is that centerpiece. That would also, you know, if you're not very fluent in applying this triangle and this geometry, then you probably struggle to see how you're going to find that. So that is how I did this drawing. I have not completed it. If I've done anything wrong here, you're welcome to say. But otherwise, that is that. I'm sort of happy with that. I just want to see if there's anything else worth mentioning here. There's a trick here, because it's classified in spec as center to center, and when we're deciding how many pieces are exposed on this eave, okay, how do I know where the next piece is? And you might say, well, it's given as center to center 345. So that's what you're going to do. You're just going to say, well, it's 345, it's within the 400, so that's okay. But the issue is it's 345 on slope, and you need to reverse calculate that. When it comes to how far does the next piece, so you've done your tilting for that, right? Okay. Now it's your batten that this comes into play. Is that, okay, your batten's actually not going to go all the way in. Okay, your batten runs like that. And you want to know what is that little bit that it's stunted by. It doesn't reach that end. Can I say that X is 345? Can I? And I would say no, you cannot. That X, since it's on flat, needs to be reverse calculated. So it's 345 centers, but because we want to know how far this timber stops before this end on flat, right? Because remember, timber's running sort of parallel with the slope. No, perpendicular. So it's running along the slope. It's not being affected by the slope. And to get its length, we can't have any slope factor involved here. So we're going to divide by 1 over cos 28 just to get this little piece on flat. So what we're saying, right, is this span over here is 345 on slope, but it's not necessarily 345 on flat when it comes to the ends of these. The ends are shortened, but they're not shortened by 345 because we're looking from the top down. We want to discount the slope, and we're going to say, okay, we need it on flat. That is a bit of a trick there with the batten lengths. So that is the story with the first batten after your tilting fillet. The other battens actually follow the same rule, by the way. We just don't sort of notice it because we don't measure or consider it because it's not exposed. We don't specifically look at it and sort of deconstruct it. But it's the tilting fillet that goes all the way and the first batten that is short. And that is of interest, and that difference is actually now divide by 1 over cos 28. So that's an interesting sort of application of the slope backwards. I want to take a look at black bolts. There's not much to say about these black bolts other than they're given as a mass out of 100. So what I've seen is mass per 100. So basically, the way I generally work is that you go 2 times 38 thickness and 2 times 10. By now you're typically using a 10 if it's 2 by 38, because this is only a 76 mil thickness. You're not going to use a M16, you're going to use a M10. Okay, so where there are instances where 2 38 millimeter thick timbers meet and you're bolting them, you've got a net, also a growth width of 76 mils. You're going to apply an M10, and you need 2 times that M10's diameter. Okay, it's 96, which you round up to 100. Okay, straightforward. Now, when it comes to calculating, now there's masses and all this other stuff. You're just going to say, well, I have 10 times, and what's It's fine. We'll say we'll have 10 by 1. And you know what the mass is per 100 bolts. So you're going to do your description. So M10 threaded, well, I just say threaded, you can say whatever you want. M10 black bolt, head, nut, 2 washers. And then what you're going to do is now add the weight if it's given. And since it's 10, you'll just say 10 times 1 over 100. And then whatever mass that is. So this is if you're using the table. But there are instances where, let's say, here's M10, and you've taken 100, which is 8.1. Okay. Now, I'm going to take a leap here and say that's typically the case. Okay. 1 over 100 times 8.1 kgs. Okay. And that'll give you mass for just 10. And when it comes to your M16, it's the same story, right? Your M16, though, is typically 150. Why I say typically is you just have to do the math and you'll see that it usually amounts to a 150. So if you have 3 times 38 thickness, and so actually we should do this first. 1, 1, 4. And since this is already over 100 mils, I instantly just say, okay, it's an M16. And you're going to have 2 16 mil lengths added to that, okay? And you're left with 146, which you're going to round up, right? 146, round it up to 150. And you end up with 150 mils, which is here. Here's your M16 column. So that is typically what I've seen. I mean, you know, there are exceptions. So 29.5, you're just going to say, well, I have 3 M16s. And you want to know what is the mass per M16, 1 over 100 times 29.5 kgs equals ... Okay, pretty straightforward. But it's extra. Now you know. And we're going to move on to batten lengths now. Let's just take a look at what we've got here. And it's not just batten, it's batten thicknesses per length. It's not batten lengths. Apologize for that. So we're going to take a rafter center to center measurement. And remember, it's maximum. So anything less than 760 mils is a 38 by 38 batten. Okay. And then what we'll say for this one is actually a 760 to 900 mils gets a 38 by 50 batten on flat. And then a 900 to 1000 is a 38 by 50 batten on edge. All we're saying is, well, since this first category is less than 760 mils, we'll get away with a smaller cross section of batten. And if we get to 760 to 900 mil centers of our rafters, so the rafters are a little bit more spaced out, okay? Let's say these are rafters here. So this is the first case, is less than 760. Then we're going to come to something that's sort of 760 to 900, and obviously I'm exaggerating this a bit. But what we need is more structural integrity in our rafters here. We're going to need a little bit more sort of tensile resistance from our timber. And the cross section needs to increase to allow for that. Okay, we've got more tiles across a given span. You know, the span is longer, but it's also having to carry a load without having a supportive rafter member here. So that's a problem. And it's solved by changing this 38 to a 50. And the difference here is this word flat. Flat means In this case, and you just need to think about this logically from a sort of engineering perspective, flat is saying this is our first upgrade from 38 by 38. And the first upgrade is not too intense. Sure, the span's increased, but it's not seriously sort of loading. It's not a serious load or jump, let's say. So we're going to add sort of material. We're going to add material in our bottom half to resist the tensile forces. We're going to increase this cross section down here, and it's going to be a 38 by 50 on flat. And it's not the strongest orientation of timber. Timber typically is stronger in sort of an upright manner, and that's why you see beams and stuff like that, so that the cross section can have a deeper sort of cross section under tension. So when you upgrade even further to a 900 mil to 1000 mil center to center of your rafter, you're going to change this to a 38 by 50 on edge. Okay, it's the same piece of timber, and this is what I had to wrap my head around. Don't be confused. It's the same piece of timber. It's just changed in orientation. I wanted to call it, well, no, now it's a 50 by 38 actually, but it doesn't change in name. It changes in orientation. So on flat is saying the larger portion of this is on flat, and on edge is saying the shorter portion is on the sort of parallel to earth. And now that the 50 is upright, what it's saying is it's kind of now acting like a little beam, and it's going to flex, but it's going to have a higher tensile resistance, okay, for loading. And that's for that longer span of 900 to 1000. So that is that with regards to battens. I'm not sure if I explained that too well, but just follow the rules and you should get it. I have seen instances where a 50 by 50 is used. I don't really understand why you would employ a 50 by 50, because my reasoning is that if this brochure tells us that you can have a 38 by 50, and then simply to upgrade this 38 by 50 on flat, you change the orientation, and now it's sort of a upgraded version of itself. But it's the same piece. Why would you go for a 50 by 50 when you have this 38 by 50 on edge as an option? You see, you're going to save material, it's more economical, so that's the one I go for. I'm not sure about justifying a 50 by 50, but we'll figure that out eventually. That is it for today, guys. I hope you enjoyed this. Bolts, don't stress too much about it. Just understand, usually you're going to go for this M10 100 mil and this M16 150 mil. Those will change. You've got to be careful with how many pieces of timber it's traveling through. The story with battens and their center to center span for the rafters, just think about that from a structural engineering point of view with regards to cross sections and how much material you're allowing under tension, because I think that's mainly what we're speaking to here. You want to increase the material that's sort of able to resist that tension, and 38 by 38 is pretty small. So that is that. The drawing, just remember, divide it into triangles. Since we've got perfect 45 isosceles triangles, 2 of those sides will be the same, and because they're the same, you're going to play around with your widths, divide your widths in half, and you'll be able to get your rafter lengths. And then the same is true for calculating pretty much your ridges and everything else. All of that hinges on the fact that these are 45 degree isosceles right angle triangles. Okay, thank you for listening. I hope you enjoyed, and I will check you guys next time.